I got a chance to read a fascinating paper you authored called Optoelectronic Intelligence. So maybe we can start by talking about this paper and start with the basic questions. What is optoelectronic intelligence?
Yeah, so in that paper, the concept I was trying to describe is sort of an architecture for building brain-inspired computing that leverages light for communication in conjunction with electronic circuits for computation. In that particular paper, a lot of the work we're doing right now in our project at NIST is focused on superconducting electronics for computation. I'll go into why that is, but that might make a little more sense in context if we first describe what that is in contrast to, which is semiconducting electronics. So is it worth taking a couple minutes to describe semiconducting electronics?
It might even be worthwhile to step back and talk about electricity and circuits and how circuits work before we talk about superconductivity.
Right, okay.
How does a computer work, Jeff?
Well, I won't go into everything that makes a computer work, but let's talk about the basic building blocks, a transistor. So, and even more basic than that, a semiconductor material, silicon, say. So in silicon is a semiconductor. And what that means is at low temperature, there are no free charges, no free electrons that can move around. So when you talk about electricity, you're talking about predominantly electrons moving to establish electrical currents, and they move under the influence of voltages. So you apply voltages, electrons move around, those can be measured as currents, and you can represent information in that way. So semiconductors are special in the sense that they are really malleable. So if you have a semiconductor material, you can change the number of free electrons that can move around by putting different elements, different atoms in lattice sites. So what is a lattice site? Well, a semiconductor is a crystal, which means all the atoms that comprise the material are at exact locations that are perfectly periodic in space. So if you start at any one atom and you go along what are called the lattice vectors, you get to another atom and another atom and another atom. And for high quality devices, it's important that is a perfect crystal with very few defects. But you can intentionally replace a silicon atom with, say, a phosphorus atom, and then you can change the number of free electrons that are in a region of space that has that excess of what are called dopants. So picture a device that has a left terminal and a right terminal, and if you apply a voltage between those two, you can cause electrical current to flow between them. Now we add a third terminal up on top there, and depending on the voltage between the left and right terminal and that third voltage, you can change that current. So what's commonly done in digital electronic circuits is to leave a fixed voltage from left to right, and then change that voltage that's applied at what's called the gate of the transistor. So what you do is you make it to where there's an excess of electrons on the left, excess of electrons on the right, and very few electrons in the middle. And you do this by changing the concentration of different dopants in the lattice spatially. And then when you apply a voltage to that gate, you can either cause current to flow or turn it off. And so that's sort of your 0 and 1. If you apply voltage, current can flow. That current is representing a digital 1. And from that basic element, you can build up all the complexity of digital electronic circuits that have really had a profound influence on our society.
Now you're talking about electrons. Can you give a sense of what scale we're talking about when we're talking about in silicon being able to mass manufacture these kinds of gates?
Yeah, so scale in a number of different senses. Well, at the scale of the silicon lattice, the distance between two atoms there is half a nanometer. So people often like to compare these things to the width of a human hair. I think it's some 6 orders of magnitude smaller than the width of a human hair, something on that order. So remarkably small. We're talking about individual atoms here, and electrons are of that length scale when they're in that environment. But there's another sense that scale matters in digital electronics. This is perhaps the more important sense, although they're related. Scale refers to a number of things. It refers to the size of that transistor. So, for example, I said you have a left contact, a right contact, and some space between them where the gate electrode sits. That's called the channel width or the channel length. And what has enabled what we think of as Moore's law, or the continued increased performance in silicon microelectronic circuits, is the ability to make that size, that feature size, ever smaller at a really remarkable pace. I mean, that feature size has decreased consistently every couple of years since the 1960s, and that was what Moore predicted in the 1960s. He thought it would continue for at least 2 more decades, and it's been much longer than that. And so that is why we've been able to fit ever more devices, ever more transistors, ever more computational power on essentially the same size of chip. So a user sits back and does essentially nothing. You're running the same computer program, but those devices are getting smaller, so they get faster, they get more energy efficient, and all of our computing performance just continues to improve. And we don't have to think too hard about what we're doing as, say, a software designer or something like that. I absolutely don't mean to say that there's no innovation in software or the user side of things. Of course there is, but from the hardware perspective, we just have been given this gift of continued performance improvement through this scaling that is ever smaller feature sizes with very similar, say, power consumption. That power consumption has not continued to scale in the most recent decades, but nevertheless, we had a really good run there for a while. And now we're down to gates that are 7 nanometers, which is state of the art right now. Maybe Global Foundries is trying to push it even lower than that. I can't keep up with where the predictions are that it's going to end. But 7 nanometer transistor has just a few tens of atoms along the length of the conduction pathway. So a naive semiconductor device physicist would think you can't go much further than that without some kind of revolution in the way we think about the physics of our devices.
Is there something to be said about the mass manufacture of these devices?
Right. So that's another thing. So how have we been able to make those transistors smaller and smaller? Well, companies like Intel, Global Foundries, they invest a lot of money in the lithography. So how are these chips actually made? Well, one of the most important steps is this, what's called ion implantation. So you start with sort of a pristine silicon crystal, and then using photolithography, which is a technique where you can pattern different shapes using light, you can define which regions of space you're going to implant with different species of ions that are going to change the local electrical properties right there. So by using ever shorter wavelengths of light and different kinds of optical techniques and different kinds of lithographic techniques, things that go far beyond my knowledge base, you can just simply shrink that feature size down. And you say you're at 7 nanometers. Well, the wavelength of light that's being used is over 100 nanometers. That's already deep in the UV. So how are those minute features patterned? Well, there's an extraordinary amount of innovation that has gone into that, but nevertheless, it stayed very consistent in this ever shrinking feature size. And now the question is, can you make it smaller? And even if you do you still continue to get performance improvements? But that's another kind of scaling where these companies have been able to. So, okay, you picture a chip that has a processor on it. Well, that chip is not made as a chip. It's made on a wafer. Mm-hmm. And using photolithography, you basically print the same pattern on different dies all across the wafer, multiple layers, tens, probably 100 some layers in a mature foundry process. And you do this on ever bigger wafers too. That's another aspect of scaling that's occurred in the last several decades. So now you have this 300 millimeter wafer. It's like as big as a pizza, and it has maybe 1,000 processors on it. And then you dice that up using a saw. And now you can sell these things so cheap because the manufacturing process was so streamlined. I think a technology as revolutionary as silicon microelectronics has to have that kind of manufacturing scalability, which I will just emphasize, I believe is enabled by physics. It's not, of course there's human ingenuity that goes into it, but at least from my side where I sit, it sure looks like the physics of our universe allows us to produce that. And we've we've discovered how, more so than we've invented it, although of course we have invented it, humans have invented it, but it's almost as if it was there waiting for us to discover it.
You mean the entirety of it, or are you specifically talking about the techniques of photolithography, like the optics involved? Or you mean the entirety of the scaling down to the 7 nanometers, that you're able to have electrons not interfere with each other in such a way that you could still have gates? Like that's enabled to achieve that scale, spatial and temporal, seems to be very special and is enabled by the physics of our world.
All of the things you just said. So starting with the silicon material itself, silicon is a unique semiconductor. It has essentially ideal properties for making a specific kind of transistor that's extraordinarily useful. So I mentioned that silicon has when you make a transistor, you have this gate contact that sits on top of the conduction channel, and depending on the voltage you apply there, you pull more carriers into the conduction channel or push them away so it becomes more or less conductive. In order to have that work without just sucking those carriers right into that contact, you need a very thin insulator. And part of scaling has been to gradually decrease the thickness of that gate insulator so that you can use a roughly similar voltage and still have the same current voltage characteristics. So the material that's used to do that, or I should say was initially used to do that, was silicon dioxide, which just naturally grows on the silicon surface. So you expose silicon to the atmosphere that we breathe, and if you're manufacturing, you're going to purify these gases, but nevertheless, that what's called a native oxide will grow there. There are essentially no other materials on the entire periodic table that have as good of a gate insulator as that silicon dioxide. And that has to do with nothing but the physics of the interaction between silicon and oxygen. And if it wasn't that way, transistors could not perform in nearly the degree of capability that they have. And that has to do with the way that the oxide grows, the reduced density of defects there, its insulation, meaning essentially its energy gaps. You can apply a very large voltage there without having current leak through it. So that's physics right there. There are other things too. Silicon is a semiconductor in an elemental sense. You only need silicon atoms. A lot of other semiconductors, you need two different kinds of atoms, like a compound from group 3 and a compound from group 5. That opens you up to lots of defects that can occur where one atom's not sitting quite at the lattice site it is, and it's switched with another one that degrades performance. But then also on the side that you mentioned with the manufacturing, we have access to light sources that can produce these very short wavelengths of light. How does photolithography occur? Well, you actually put this polymer on top of your wafer and you expose it to light, and then you use a aqueous chemical processing to dissolve away the regions that were exposed to light and leave the regions that were not. And we are blessed with these polymers that have the right property where they can cause scission events where the polymer splits where a photon hits. I mean, maybe that's not too surprising, but I don't know. It all comes together to have this really complex manufacturable ecosystem where very sophisticated technologies can be devised, and it works quite well.
And amazingly, like you said, with a wavelength at like 100 nanometers or something like that, you're still able to achieve on this polymer precision of whatever we said, 7 nanometers.
Yeah.
I think I've heard like 4 nanometers being talked about, something like that.
Yes.